A biochemist developing a new compound to lower blood glucose faces an immediate logistical wall. They cannot administer their experimental drug to millions of diabetic patients to see if it works. They are restricted to testing a sample of 30 individuals, while their goal is treating a biological population numbering in the tens of thousands. This creates the core problem of biological variability. If you repeat the exact same experiment on a different group of 30 patients, you will naturally record a different average glucose reduction. Researchers rely on descriptive statistics to handle the raw data in front of them. These mathematical tools, like mean, median, and range, are used exclusively to describe the specific sample tested in the lab. To bridge the gap between those 30 patients and the millions outside the lab, researchers use inferential statistics. This is a distinct mathematical framework required to predict the reality of the untested population based on the limited sample data. Because we can never measure everyone, inferential statistics is strictly the science of making decisions in the face of absolute uncertainty. Without mastering this mathematical bridge between description and inference, a scientist cannot prove a biological mechanism is anything more than random environmental noise. The first conceptual hurdle in reporting experimental results is distinguishing between two heavily conflated metrics, standard deviation and standard error. Standard deviation, or SD, is the measurement of biological variability within the raw data of a sample. This dot plot shows the SD of enzyme activity across 25 subjects. The wide dispersion illustrates the exact amount individual subjects, like rats or cells, differ from one another in nature. Standard error, or SE, serves a completely different function. It measures the calculated precision of the researcher's estimate of the true population mean. As this equation shows, standard error is calculated by taking the sample standard deviation, S, and dividing it by the square root of the sample size, N. The result is a much tighter boundary that quantifies our confidence in the true average. Notice the inverse exponential relationship. As the sample size increases, the standard error physically shrinks. To cut your error in half, you must quadruple your sample size. For scientific publication, these metrics cannot be swapped. SD must be used to show the natural biological spread of the subjects. SE must be used to show the researcher's confidence in the actual experimental effect. Researchers cannot control inherent biological standard deviation. They can, however, artificially control their standard error through rigorous experimental design and careful sample sizing. In statistical analysis, every experiment operates like a criminal trial. The null hypothesis is the baseline presumption of innocence, the mathematical assumption that an experimental drug or condition has absolutely zero effect. Because science relies on incomplete sample data to render a verdict, experimental decisions inherently contain mathematical failure states. These failure states must be quantified. This 2x2 grid illustrates the decision matrix. It maps the absolute truth of the null hypothesis in nature against the researcher's final experimental conclusion in the lab. A type 1 error, designated by the Greek letter alpha, is a false positive. This occurs when a researcher mathematically rejects a true null hypothesis, concluding there is an effect when none exists. The consequence of a type 1 error is severe. A company might waste millions in funding and years of research on a biologically useless drug. A type 2 error, designated as beta, is a false negative. This happens when a researcher fails to reject a false null hypothesis, concluding there is no effect when one actually exists. In practice, a type 2 error means missing a critical discovery, such as failing to detect a toxic compound actively present in a public water supply. To avoid false negatives, researchers calculate statistical power. This metric is the direct inverse of a type 2 error probability. Power is the mathematical probability of correctly detecting a biological effect, assuming that effect truly exists in nature. Small sample sizes physically limit the mathematical possibility of detecting an effect. If your sample is too small, your statistical power drops, dooming the experiment to a false negative before data collection even begins. Rigorous experimental design is the deliberate act of balancing the acceptable risk of a false positive against the power required to avoid a false negative. Navigating these errors requires a strict threshold for evidence. In published scientific literature, that threshold is almost universally the p-value, the most heavily relied upon yet widely misunderstood metric in biochemistry. This distribution curve visualizes the strict mathematical definition of the p-value. It is the probability of obtaining results at least as extreme as those observed, assuming the null hypothesis is perfectly true. The p-value solely measures the probability of obtaining your specific lab data, assuming the baseline state of no effect is absolute reality. It does not measure the probability that the null hypothesis itself is true or false. It also does not measure the probability that the researcher's alternative hypothesis is correct. The metric is purely a measure of data compatibility. It asks, how unusual is this data if the baseline assumption of no effect holds true? Misinterpreting this metric leads to a widespread systemic flaw in modern research called p-hacking, the practice of manipulating data or analyses until non-significant results become significant. Running statistical tests repeatedly on the exact same data until a p-value drops below 0.05 destroys the mathematical validity of the threshold. It guarantees a type 1 false positive by sheer attrition. Treating the p-value as definitive proof of a biological theory is a logical error that routinely invalidates published research. This brings us to the final analytical trap, conflating statistical significance with practical, real-world importance. On the left side of this split-screen chart, we have a clinical trial for a blood pressure drug. The data shows a highly significant p-value of less than 0.001. However, the actual drop is a microscopic fraction of a millimeter. It yields a significant p-value purely because the sample size is 10,000 patients. The result is mathematically real, but clinically useless. But on the right side of the screen, we see the inverse scenario. A cancer drug trial demonstrates a massive 50% reduction in tumor size, yet the p-value is 0.12, mathematically not significant. This 50% reduction yields a non-significant p-value because the experiment only used 5 mice. It lacked the statistical power to verify the effect. To prove the actual magnitude of a discovery, researchers must report effect size alongside their p-values. A common metric is Cohen's d, which calculates the standardized difference between two means to show exactly how large the biological impact truly is. Researchers must also report confidence intervals. A confidence interval provides a precise numerical range of plausible values for the true population parameter, moving the conversation from a binary yes or no to a definitive measure of precision. Robust scientific truth cannot be captured by a single probability score. It requires the context of p-values, the magnitude of effect sizes, and precise confidence intervals to prove a mechanism is both mathematically real and biologically relevant.